actually very low, again showing the presence of a solar cycle. And these X-ray flares are deeply connected to the presence of magnetic fields of the sun. So, magnetic fields are present everywhere in the universe. Now, Earth has it, Sun has it, and then there are other systems in our Sun is a star. So other stars also will have magnetic fields. There are special kinds of stars called pulsars, supernova remnants. We'll come to that in a minute. The whole galaxy, our Milky Way galaxy, also has magnetic fields. Weak, but still present. And then there are galaxies that are different from our galaxy. Galaxies where you have very large black holes. I mean, our own galaxy has a black hole. But there are galaxies where 1,000 times more massive black holes exist. Those are often called active galaxies. And these active galaxies, sometimes called quasars, are also places where magnetic fields play a role. And there are things called gamma ray bursts. Some of you may have heard about fast radio bursts, a subject of intense discussion these days because we don't understand what it is. And then there are things called clusters of galaxies. Galaxies themselves form clusters. There's gravitational force is infinitely long. So in principle, you are influencing every other object in the universe. And so galaxies can also be gravitationally bound, and the largest such structure is what we call as a cluster of galaxies. So even such places you have magnetic fields. And between galaxies, and of course the early universe has magnetic fields. So we will try to cover some of these things in this short talk. Next one, please. So this is a picture of our galaxy. Now you have to understand how, as somebody said in the morning's program, how do you take a picture of our galaxy when we're sitting inside the galaxy? I mean, 100 years ago, this was a big puzzle. What is the shape of our galaxy? Is it spiral? Is it an elliptical galaxy? It was very difficult to see because you can't go outside the galaxy and look at it. You're sitting inside the galaxy and trying to find the shape of the galaxy. So this picture is a picture where you would, if you remember, it's a spiral galaxy, and we are not at the center of the galaxy. We are at, say, 2/3 of the distance from the center is where Sun is, and around the Sun is where we are sitting. And from there we take a picture. If you sit from there and look at the center of the galaxy, that will be the center of this picture. And if you look away from the center of the galaxy, that will be the two edges. So the two edges actually connect. So that's how to look at this picture. And if you look above and below the galaxy, below this, in this picture, what you see is regions that are outside the disk of the Milky Way galaxy. So you're actually seeing the extragalactic universe. The whole universe is visible to you. So this is a picture of the whole universe. However, using this specialized satellite, in this case called Planck, it's a European Space Agency satellite called Planck, which is used to study the microwave background of the universe. They mapped the magnetic field lines of the galaxy. And you can see the disk of the galaxy where all the stars are, all the masses, matter, gas is present. It is very strong in magnetic fields. And so there is galactic magnetic field. However, at a level that's much weaker. So we said, what was the strength of the field in this room? 1 Gauss. So this is about 1/1,000,000th of that, 10 to the minus 6 Gauss. It's micro Gauss. So galaxy in the space between stars, you have fields that are at 1/1,000,000th of a Gauss. You think it's very weak, but it's actually very important because, imagine a charged particle like an electron or proton coming from a star that's far away in our Milky Way galaxy. As it comes, because of the magnetic field, it will not come straight, it will actually bend in the magnetic field. So you can never tell where the charged particle comes from. That is why we don't have charged particle astronomy. I can't tell where it's coming from. Whereas a photon, a light particle, has no charge, and the magnetic field doesn't influence it. So that's how we're able to make a map of the galaxy, because it's no charge. Next one, please. So, and then there are many things in our galaxy that also have possess magnetic fields. Now, I mentioned to you earlier when we were discussing the sun that plasma, that is ionized matter, and magnetic, when you put them together, they are like good friends. One moves, the other moves with it. So when the gas in a nebula, in an early universe, and before the sun formed, there was a lot of gas in our solar system region. And the gas collapsed under what force? Gravity. And that was the only thing. Gravity collapsed. when gravity collapses and the matter comes together, atoms become close to each other. Not only atoms come close to each other, magnetic field also comes close to each other. So what happens is the strength of the field increases as it gets smaller and smaller and smaller. Whatever was the total field in that whole gas, now it gets concentrated into a small region. So when stars form from this gas, stars typically have magnetic fields because the matter from which the star formed already had magnetic field. And so when the star becomes very compact, have you heard of things called neutron stars? So it's a star where regular atoms, which has a positron, which has a proton and an electron. Imagine as though somebody made it so tight that the electron is pushed into the proton and they neutralize and they form a neutron. So if you make a star with neutrons, then they can be very dense. And that is what happens when the strong gravity plays a role. It happens when stars explode. A star explodes, a massive star explodes, it actually blows away a lot of gas and material outward, but there is also an inward pressure, and that inward pressure compresses matter and makes regular atoms into neutrons. So these neutrons form, and the neutron stars are stars made up of completely neutrons. So they can be very dense. How dense can you imagine? What is the density of water? 1 gram per cc. So a neutron star will have a density of 10 to the 15 grams. 1 followed by 15 zeros grams per cc. Because imagine our sun, the whole mass of our sun, if we compress it into the city of Kochi and Ernakulam. That's what a neutron star is. Incredibly dense. And when it compresses, as I told earlier, it also compresses the magnetic field. And so the field is not lost, field goes with this matter. And so the strength of that field is now 10 to the 8 to 10 to the 14 Gauss. So let's go back to the strength of the field in this room is 1 Gauss. In the space between stars it is 1 microgauss. But now we have stars, or special kind of stars called neutron stars, where the strength of the field is 10 to the 15, it can go up to 10 to the 15 Gauss. Extremely strong fields because it is collapsed in the matter from which these stars form. So that is what is called a pulsar. And then they spin because when that matter from which the star formed already had angular momentum. And you have studied conservation of angular momentum. It has to be conserved. So as star shrinks, it spins very fast. Extremely fast. Sometimes in 1 millisecond it completes one rotation. Our sun takes how long to rotate? Anybody knows? Once around its axis. 27 days. But there are stars that rotate about itself in 1 millisecond. So it's incredible. So when that happens, and if the spin axis is different from the magnetic axis, then it's like a light beam. It comes in our direction. And every time you can measure the light beam. And that is why it's called a pulsar. And these pulsars are very precise. Some of the best clocks in the universe are pulsars. You can measure its precision down to 10 units and better as a fractional time. So pulsars form, and once again, when they radiate, you see light from it, and that light is also coming because of the strong magnetic fields. So I just want to emphasize the fact that you can have fields now as strong as 15 Gauss. This is an example of what is called the Crab Nebula. You heard of the Crab Nebula? Some of you may have heard of it. It is called, and what is it? Supernova, which means it's a remnant of an exploded star. And this was actually very famous because it's only 1,000 years ago. In 1024, Chinese astronomers actually marked this, saying that there was a star as bright as the sun during the daytime. So you can imagine how bright a supernova is in the early phases. And what you see is all these filamentary structures. That's why it's called like a crab, like it's a crab. But these filamentary structures show emission of light. And that light actually comes because of a process called synchrotron radiation. We'll come to that in a minute. Again, it is because of the presence of magnetic fields, and particles that move around magnetic fields tend to radiate light. And that's the light we've seen. Okay, next one please. Then I mentioned these galaxies that are called active galaxies. So they are active compared to normal galaxies. Our Milky Way is a normal galaxy, even though it has a black hole at the center. And that black hole is about 1,000,000 times the mass of our sun. Now, active galaxies are things where I mentioned it may be 100 times more massive than that. So 10 to the 8, 10 to the 9 times the mass of our sun. Extremely large black holes. And when they are present in the center of a galaxy, it will pull a lot of matter into the center of the galaxy. So it's radiating, matter falls into that. Matter falls into it, gets heated up. And that hot gas radiates. When the gas gets hot, it radiates, right? So you have studied black body radiation. Black body radiation says for an object at a given temperature, we can precisely tell what's the shape of the spectrum coming from it. How much light will come at any given wavelength. When the temperature is very large, when the temperature is about 1,000,000 degrees Kelvin or 10,000,000 degrees Kelvin, most of the light comes out in X-rays. So what you see is also black body radiation. So at the center of these galaxies, and I've zoomed in into that, and that is what you see. This is a galaxy called Centaurus A. Centaurus A is very important because it's the nearest active galaxy to Earth. And so we are able to study it. On the sky, if you look, it's actually a very big object. It's 8 degrees wide. I mean, that's massive. And but you can only see this if you're looking at it in radio waves. The radio waves will measure this best. But the center of that, you can see there are 2 jets coming out on either side of it. And that is the result of when matter falls into the center of these large black holes, so much energy comes in, it has to channel it out somewhere, and it channels it out 2 jets. And for it to be symmetric, so it actually have a forward jet and a backward jet. And in these jets, what you see is particles are being thrown away, it radiates from light, and this goes on over large distances. And so those are called, such galaxies are called active galaxies, and they typically have this jet structure in which particles are being accelerated. I'll give you another example, next one. This is what is called Cygnus A. It's a very famous radio source. And what you see again is the central black hole has this bright dot, also a very massive black hole. But you see 2 lines, and this happens to be a case where you're directly looking at it almost perpendicular to its orientation. And each of those lines is about 250,000 light years. Whereas our Milky Way, any idea how big our Milky Way is? It's about 100,000 light years. So this is much bigger than the Milky Way. And at the end of that, it looks like what we now believe is that at the center of the black hole, it accelerates particles like electrons and protons and positrons. Positrons are what? Antiparticles of electrons. So we think, actually we don't know what is in this jet, but all that accelerates, and then as it loses energy, it expands in this big, what is called the radio lobe. And so all of this is visible. But look at the scale of this. It is so big. These jets are going outside the galaxy in which it is sitting. And what makes it so narrow? That's where I ask the question. What channels plasma over long distances? We believe it is again magnetic fields. So we have like a cover of magnetic fields in which these particles are being blown away over such incredibly long distances. Okay, next one. So let's just look at our charged particles. The simple thing that we learn is this. You have a positively and negatively charged particles, and you have a magnetic field that is, say, in this case, going into the field, into the board, then they will deflect in opposite directions. Charges are, so a positive charge will deflect different from a negative charge. Next one. Now, so if I have a field going in this direction and there's a particle sitting here, what happens to the particle? Let's say an electron is sitting here. There is a field, a magnetic field, I switch on the magnetic field. What happens to the electron? Any idea?
It is moving like, it is a velocity that is very high.
Right, but if there is no velocity, what happens? There is zero velocity. It will sit there. Nothing happens. If it has a velocity, and if the velocity is only in this plane, then it will go in a circle. And that is what we call a cyclotron, synchrotron. There is a very famous synchrotron in Indore that Atomic Energy Department of Atomic Energy has made. All that work on that principle, yeah. But if the particle has a small velocity component in the direction of in any other direction, then it will not be in a circle, it will move in a helix. Like this. And that is what I'm showing here. With a small velocity component in the direction of the movement, then it moves like a helix. So particles which have, so it has both velocity vector in the plane perpendicular to the magnetic field as well as in the direction of the magnet. Next one, please. So now if I have a system where the magnetic field is not uniform but actually expands and it contracts, where you have strong fields at one end and strong fields at the other end, and a weak field in the middle, what happens is particles will gyrate, but as the field becomes stronger, it actually will, its velocity in the direction of the field will actually slow down until it goes to zero. And then if the field is any stronger, it actually gets a kick backwards. So the particle goes from this side, comes here, stops, and then you'll have a force in the other directions will move back and keep going back and forth. So this is what's called a magnetic bottle. You've heard of tokamaks? Fusion reaction. I heard, maybe you haven't, but there is an Institute of Plasma Research in Gandhinagar in Ahmedabad, which actually, in Gandhinagar, which actually has created these tokamaks. Fusion reaction is something we would like to really use for energy production, right? Fission we already have, our current nuclear reactors do that. But fusion is considered cleaner, better, and one of the challenges of fusion is how to hold the plasma without touching the walls of the fusion reactor. Because if we touch the walls, the plasma will get neutralized. And the way they do that is by using things called magnetic bottles. The plasma doesn't touch it, it keeps circling between the two ends, and that is how they create what's called the magnetic bottle. Okay, next one. So now there are magnetic bottles in nature also. For example, have you heard of Van Allen belts? Remember in the 60s when we started exploring space, people, even the first set of rocket spacecrafts, they were putting detectors, particle detectors. The detectors that can detect the presence of protons and electrons. So a very famous scientist called Van Allen, who was heading the US Explorer program. And when one of the flights came back, they found a lot of radiation, a lot of charged particles, and then there was a story that went around saying radioactivity is all over, space is radioactive. We cannot go, it's incredibly dangerous. Now we understand that yes, there are some places where space radioactive, particle influx is high, and we call those as trapped radiation belts. And they're named after Van Allen, called the Van Allen radiation belts. These are shown in this cutout section. Earth is there. Remember, Earth is as a magnetic field, that's like a dipole, like a regular bar magnet. And so when a bar magnet has it, if you look at the field, it actually has a field where the field is initially very strong at the pole, then it becomes weak, then again becomes strong. Now in the previous slide I showed you how a particle moving in that tends to bounce between the two ends like a bottle. So these are called trapped radiation belts. The particle is trapped in it, it cannot escape, it stays there. And the particle comes from the sun. Every time the sun undergoes an explosion, it will contribute some particles to this radiation belts. And the particle stays there. And so there are two belts, one made up mostly of electrons, the other made of protons. Now, when you want to go to the moon, you have to cut through this belt. Our small regular satellites called low Earth orbiting satellites, LEO orbits, you don't have to worry about it because they are below the radiation belts. But even our geostationary satellites, our communication satellites, have to cut through this belts. But when you have human beings going in it, tomorrow you have to go in that satellite, you want to go to the moon, you have no choice but to cut through this radiation belt. When you cut through radiation belts, you worry about radiation on the biology, what happens to you. When Neil Armstrong went there was a competition so intense, they were willing to take a lot of risk. So they went there irrespective of, we weren't willing to die for it because if the sun had exploded, maybe they may not have survived. So cutting through this radiation belt is critical. And so even when we are flying Chandrayaan 1 and Chandrayaan 2, we go through a process of increasing our orbit so that we make sure the orbital parameters are correct. But then if we have too many such orbits around Earth, we will have too many crossings of the radiation belts. The experiments on the satellite will all get damaged. Satellite system itself will get damaged. So it's a tricky thing to minimize the exposure to radiation belts when you're planning missions outside Earth. So I'm just trying to show once again that the presence of magnetic fields is omnipresent, everywhere is there, and we need to worry about how best to tackle it. Now, these radiation belts, as I mentioned earlier, are not steady. They tend to change in time. So when there is an explosion, look at the last figure. It fills the whole section area around Earth. So you need to be worried. As many of you in future, as humans will go into space, many more often than today, you have to worry about this. You have to, just as you check today, is it going to rain today? Is there going to be snowstorm in other parts of the world? You have to check what is the space weather if we go up. And this is precisely the weather that SpaceX did not do when they lost 40 satellites, because they didn't check the weather and they miscalculated and something. So this region around Earth is actually very dangerous. You need to make sure that the radiation belts are indeed at a reasonable size before you venture out. Next one, please.
Sir, what if we are going for a pole in a polar?
Say that again.
We are starting from a pole and going in a polar orbit.
You will still have, in the sense, see, polar orbit, that the region of the polar orbit is very strong in radiation because it's a place where the belt comes very close. You can do up to some point, but the point still is you will be cutting into it. The amount of particles in even what you see as this wide section in the equator will all converge into a small point. So you'll get it in high dose for short periods of time. No escaping it. So there are processes. So next one please. Yeah. So why? On one hand we have magnetic fields, and why do we need to study these things, or how do we study these things? It turns out that the way we study is by looking at the light that comes from it. So when there is a magnetic field and a particle moves around, it is accelerated, right? Anything that goes in a circle is accelerated. Whenever a charged particle accelerates, it always radiates. So it radiates, and that comes as radio waves, and we actually pick them up. So that is what is called synchrotron radiation. If the energy of the particle is very high, it can radiate not from synchrotron, not a radio, it can be radiate X-rays. And so there are facilities called synchrotron labs, synchrotron facilities, as I mentioned earlier. Indus 1, Indus 2 are two facilities in Indore, run by the Raja Ramana Center for Advanced Technology, of Atomic Energy, where people go there to use it to study crystals, crystallography, composition, many things, and also sometimes used for radiation therapy. Next one, please. You also have things called reconnection. Reconnection, and the most famous place where you see reconnection is on the sun. And I have mentioned to you about the solar flares. The solar flare is nothing but a case where, when this twisted field that we spoke about earlier, when it becomes so strong, and you have situations like this where in red you are seeing magnetic fields going in one direction, in blue you are seeing it going the other direction. When these sort of opposing magnetic fields are pushed together, is unanswered as of now. And it's a question for many of you to worry about. Next one. Alright, so I want to close with this slide. And it says that we know the solar system now. It has so many planets, but there's only one where we have such conferences going on right now, as far as we know. And that is in the habitable zone. Habitable zone is a zone where water exists in the form of a liquid. And Venus is not far away. We still don't understand why Venus is not supported life. Maybe it did. Mars is possibly also in the habitable zone. Next one. But after some time, the sun, as it totally evolves, right? Sun is not going to be steady. Sun will become a red giant, big star. When the sun becomes a red giant, habitable zone will move where Jupiter and Saturn will be part of the habitable zone. Of course, we may not be around at that time, but clearly there is an implication. And that's important because in the last 25 years, one of the big discoveries has been the discovery of planets outside our solar system. And there are a large number of them, right? We must have heard of exoplanets, planets where planets orbiting other stars. And now there are so many, now we think pretty much almost half of the stars must have planets, and not one planet, maybe many. So they have solar systems around many stars. If there are solar systems around many stars, what makes it not viable that there will be life on these planets? Have you heard of this famous equation called Drake's equation? Francis Drake, who just died just recently, had in the 1960s made an equation that showed we calculate the probability for life to exist in the universe, life other than the life on Earth. and he multiplies a series of probabilities. Probability for a planet to have a star to have a planet, probability for the planet to be in the habitable zone, and the planet probability for that to have life, and probability for the life to evolve into complex insects, etc. If we now look at those numbers, it's not equal to zero. So the probability is not zero, probability is something. That is an important issue, and in that context, we really have to ask this question about why and how life originated on Earth, and what protects us. One of the key elements of protection of life on Earth is the fact that Earth has a magnetic field which actually shields us from the large amount of particles that come from the sun, and that protection. So the question in front of us is that a necessity to address this holy grail question, which is there life outside Earth? That is something everybody would be interested in. That is something I would imagine is one of the most fundamental questions to answer. And tomorrow when you detect it, it will create a whole new revolution about what to do when we see life elsewhere. So that's an important question. That's something many of you may want to pursue in your future careers. So I'll stop there and answer any questions you might have. Thank you.
So നമുക്ക് ക്വസ്റ്റ്യൻ ആൻസർ സെഷനുള്ള ടൈമാണ്. നിങ്ങൾക്ക് ആർക്കെങ്കിലും ക്വസ്റ്റ്യൻസ് ചോദിക്കാം. എത്ര വലിയൊരു എക്സ്പെർട്ട് പേഴ്സണാലിറ്റി നമ്മുടെ മുന്നിൽ എത്തുമ്പോൾ നമുക്ക് ഏറ്റവും നല്ലൊരു ഓപ്പർച്യൂണിറ്റി ആണ് നമ്മുടെ അറിവ് വർദ്ധിപ്പിക്കാൻ. സോ നിങ്ങൾ കൈവന്നിച്ച മൈക്ക് കൈമാറാം, അവർക്ക് നേരിട്ട് ചോദ്യങ്ങൾ ചോദിക്കാം.
സർ, ഒരു ചെറിയ സാറേ, ഞാൻ ഭയങ്കര ഹലോ. നമ്മുടെ ഇന്ത്യൻ സയൻസ് കോൺഗ്രസ് ഒക്കെ വരുമ്പോഴേ ആളുകൾ ഇതൊക്കെ സംസാരിക്കുമെങ്കിലും അവസാനം ബ്രഹ്മവിഷ്ണു മഹേശ്വരൻ എന്നുള്ള സങ്കല്പത്തിലേക്ക് കൊണ്ടുവരും. ഇതിലൊരു വാസ്തവമാണ്.
ഞാൻ ഈ ഇത്ര നാള് പലതും നമ്മൾ പഠിച്ച് വരുമ്പോഴും one of the most important things we now learn is നമുക്ക് പലതും അറിയില്ല. More we know, the less we realize എന്താ അറിയാവുന്നത്. So there is still an issue about what is nature rules and regulations and evolution, പലതും അറിയില്ല. So unknown content is still very high. അത് നമ്മുടെ ബാക്കിയുള്ള ഡിസ്കഷൻ തമ്മിൽ ബന്ധമുണ്ടോ എന്ന് ചോദിച്ചാൽ അത് എനിക്കറിയില്ല. But there is room for discussions and there is a need to really continue to explore this. അത്രയും പറയാൻ പറ്റും.
So next are
അന്ന് കുറെ ചോദിച്ചായിരുന്നു അത്.
I have two questions. First question is that you've shown a map of a Planck satellite which taken map the whole magnetic field. I think the Planck satellite is working on microwaves. So how do we map all the strong magnetic field, since the synchronous radiation and all in X-ray mainly? But how we...
So what you do is Planck's primary objective is to look at the microwave background. So we did that. But when they try to study that, you also find that the dust in the galaxy is affecting the polarization of the microwave radiation. And the dust tends to align itself to magnetic fields. So it's an indirect way to derive the magnetic field. So this was not its original objective, but it's been a beautiful result. And we haven't had such a map. The synchrotron also provides radio. You can actually see the presence of fields, but this is the most detailed map because of the dust polarization.